5.3 is probabilities using counting methods. So we're going to figure out probabilities, and we're going to look at questions where you can use combinations, fundamental counting principle, or permutations. In some cases, when you're doing these with the probability, you're going to be able to either use permutations or combinations to figure these out. And you can just decide which way you prefer to do. The first couple examples that I'm doing on the board here, if you look in the textbook, they have two ways of solving them, one using permutations and one using combinations. I think I do a bit of both, I can't remember. So on page 314 in your textbook, or 313 is where this starts. 314 is where some of these problems that I took are from. So the first one says, Jamal, Ethan, and Alberto are competing with 7 other boys to be on their school's cross-country team. All the boys have an equal chance of winning the trial race. Determine the probability that Jamal, Ethan, and Alberto will place in the top 3 in any order. So does order matter in this? Well, yes, kind of it does. But because you're choosing them from a group of, 10 people, you can look at this as a combination problem. I'm going to do it as the combination. In the textbook it shows you how you could solve it using permutations. In the case of the permutations, if you say that yes, it is a permutation, your reasoning for that would be because one of them has to be in first, one of them has to be in second, and one of them has to be in third. So then that means that the order matters in which they go in. If you're just selecting, in this case, where it's just saying we want the probability that they're going to be in the top 3, then we're looking at a combination, as in the Chinese food combination. Pick your top 3. Well, that's a combination. Order doesn't matter. It doesn't say so-and-so has to be in first, so-and-so has to be in second, and the other person has to be in third. So depending on how you look at the question, you can answer it in either way. So in this case, I'm going to say, does order matter? Somewhat. But it's not specifically in here that you have to have it in a certain order, or that each boy has to be in a certain spot. So because we're saying it's a somewhat, it's not a definite yes it does, we're going to go with the combinations. My writing's very messy. If you say yes definitely, which you can answer this with a yes definitely, order matters, then you can do permutations. And like I said, if you look at the example on page 314, it'll show you that. So if we look at this as a combination, says there are blank ways in which 3 runners can place in the 3 positions. So top 3 positions, we have first, second, third, so there's 3 positions, and we're looking at choosing 3 people to go in those positions. So it would be 3 ways of doing that. So if you remember for combinations, it's n factorial over n factorial times n minus r factorial. And you can just punch it into your calculator too, but it's always good to keep that in mind in case a question asks you to expand. So 3c3 would be 3 factorial over 3 factorial times 3 minus 3 factorial, which is just basically 3 factorial over 3 factorial, so that is 1. So if we look at this as outcomes, there's one favorable outcome where you can pick 3 people and put them in the top 3 spots, and that only makes sense. So if we take a look at the second part, there are blank ways that the 10 runners can be placed in first, second, or third. So remember when we're looking at favorable outcomes, or if we're looking at probability of favorable outcomes, it's the favorable outcomes out of all the possible outcomes. So that's why for this one we need to do this, okay, well, how many ways are there to pick or choose 3 people to be out of 10 to be in the top 3? So that means that out of 10 possible people, we're only choosing 3 of them. So 10c3 is equal to 10 factorial over 10 factorial times, sorry, not 10 factorial, 3 factorial. Oh, when I put that there too, that should be an r factorial. Ten factorial over 3 factorial times 10 minus 3 factorial. So that's 10 factorial over 3 factorial times 7 factorial. If you do that in your calculator, that equals 120. So that means that there are 120 possible outcomes. So the possibility of our favorable outcomes, which is that all 3 of these guys placed in the top 3, is the number of possible outcomes, or favorables, over number of possibles. So we had 1 out of 120, so that is 0.0083. So as a percent, that is 0.83%. So it's a pretty slim chance that those 3 will end up in the top 3, just based on choosing them, not based on their statistics as their personal bests or any of that. Okay, we're going to look now at doing a problem using the fundamental counting principle. So if you remember, the fundamental counting principle is looking at each of the possibilities and you multiply them together. So it says Channing has 3 children. Determine the probability, of Channing has at least 1 boy. So at least 1 boy means he could have 1, 2, or 3 boys. So if you think of this in fundamental counting principle, if we did the tree, well, his first child would be a boy or a girl, so that's the first. The second child then, after he had a boy, well, that could be a boy or a girl. If he had a girl first, then he could have a boy or girl second. So this is his second child. For his third child, if the second one was a boy, then the third one could be boy or girl. If it was a girl, the second was a girl, then the third could be a boy or girl. Same thing there, and same thing there. So those are the possible combinations. He could have a boy, and a boy. He could have a boy, a girl, a boy. He could have a boy, and a girl. He could have boy, girl, boy. So there's all these possibilities that he could have. So then all together, all the possible outcomes then, okay, so if we count these, there are 1, 2, 3, 4, 5, 6, 7, 8. So counting our bottom row here, there are 8 possible outcomes that he could have. If you think of this using fundamental counting principle without the tree diagram, where he's got 2 possibilities for the first, 2 for the second, and 2 for the third. So that equals our 8. So the probability of at least 1 boy which is the same as having 1 or 2 or 3 boys. So if it's an or, then I know I am going to add them up. So what is the possibility of having 1 boy? It's 1. Possibility of having 2 boys, so there's another 2. So 1, I'll just write it under here. So it'd be 1 plus 1, 2 plus the possibility of having 3 boys. So all I'm doing is counting my boys up on my tree diagram here would be 1, 2, 3, 4. So altogether then the possibility of having 1 or 2 or 3 boys would be 3 plus 4 is 7. And that, I shouldn't even write that as the probability yet. That's just having at least 1 boy. So I did this by counting up on my tree. You could do this by doing the permutations. Okay, so if you have 3 kids, then the first one would be 1 boy, 2 girls, so you do 2p1 plus 2p2. The other one would be oh, and then, sorry, yeah. You have to do the permutation for each one of the 1, 2, or 3, and then add them up. So this is just a little bit quicker in this case to actually draw it out because I can just count them. So the possibility then, or the probability of at least 1 boy, so that's all the possible outcomes at work, so favorable outcomes over a possible, so it's 7 over 8. So that works out to 87.5%. Sorry, those two kind of ran into each other. So that's doing it if I did that. Okay, so if I have at least 1 boy, 1, 2, or 3. The other way to do it is to look at the outcomes the exact opposite. At least 1 boy, well, let's go no boys, so all girls. So probability, then, if you look at this, that the outcome where you have 1 girl, so that's an and. That's an and situation. I want 1 girl and 1 girl and 1 girl is what I'm looking at. So I have 1 here, 1 here, and 1 here. So that's just 1 times 1 times 1, or 1. So the probability of that, probability of all girls is 1 out of all of the possible outcomes, 8. So then what I could do is, knowing that probability of having all girls, which would be 0 boys, means that if I take away this probability from 1, remember my probability is always between 0 and 1, so probability of all boys, to figure it out in another way, is taking 1, the most I could have, most probabilities, over or minus probability of having all girls. So that would be 1 minus 1/8, which is 7 over 8. So I get the same answer. So if you have that at least 1 situation, then you can look at it as doing the 1 minus probability of not having any of them or all of the other kind. Okay, so the next example is probability using some reasoning. So you're not, I mean, we are going to still follow a formula, but it's not necessarily looking directly at permutations or at combinations. It's still using, though, our factorial notation to solve. So it says, Bo hosts a morning radio show in Saskatoon. To advertise the show, he is holding a concert at a local mall. He spells out Saskatchewan with letter tiles. Then he turns the tiles face down and mixes them up. He asks Sally to arrange the tiles in a row and turn them face up. If the row of tiles spells Saskatchewan, Sally will win a new car. Determine the probability that Sally will win the new car. So if we take a look at this then, there are a total of 1, 3, 6, 10, 12 tiles. So there are a total number, that's our total number of tiles. Then we look for repeats. So we have 2 S's that repeat, and 1, 2, 3 A's that repeat. So that means that we're left with 7 other letters. So our total number of ways of arranging these, and because we're not picking them one at a time, we're picking them all at a time, then what we're looking at is, okay, we have 12 tiles in total. That's how many we can select, but we have 2 S's that repeat, 3 A's that repeat, and 7, oops, sorry, we don't need that 7 there. That's just our other letters. So our total number of possible arrangements over our repeats. So that equals 39,916,000 16,800. So now we have all of the possible outcomes. How about the number of favorable outcomes? So the total number of ways to spell Saskatchewan, if we call that R, is 1. There's only one way to spell Saskatchewan. So if I take a look at the probability of her winning the car, it's the probability over the right ways over all of the ways that could be selected. So it is 1 over 39,916,800. So chances are quite unlikely that she's going to win that car. Okay, so continuing with solving probability with some conditions. There are 18 bikes in Marnie's spinning class. The bikes are arranged in 3 rows, with 6 bikes in each row. Allison, Brett, Carol, Doug, Erica, and Franco each call the gym to reserve a bike. They hope to be in the same row, but they cannot request a specific bike. Determine the probability that all of the friends will be in the same row with Allison and Franco at either end. So when we're looking at this, this is an arrangement. We're trying to arrange these people so that they can be beside each other in a row, all together in a row. The only stipulation is Allison and Franco have to be in particular spots. So if we take a look at this and pretend that each of these boxes represent a bike, then if we say if Allison's going here, and bike number 2, we'll call this one, is Franco's going there. So we've used up person 1 and person 2. That means that there are four different people can go there, 3 there, 2 there, 1 there. Now in these other seats then, these other bikes, we have all the other people that can go there. So we have person 1 can go there, 2, 3, 4, or if we, I guess it could have started here and said there's 12 people can go there, 11, 10, 9. Doesn't matter which way you start this. Okay? So those are 3 rows. Allison and Franco on either ends. The other 4 of the 6 friends can go in whatever arrangement there. So the number of ways to seat Allison and Franco at either end, well, I can put Allison on the left, Franco on the right, or Franco on the right, Allison on the left. Did that even change? Franco on the left, Allison on the right. So I have 2 factorial, or if I think of it as a permutation, it's 2p2. So number of ways to seat the other people. Well, if I've taken those 2 out of there, that means I've only got 4 other people to seat and 4 ways to put them. So that's just a 4 factorial, or 4p4. I'm taking 4 people and I'm arranging all 4 of them. The number of ways to seat the other 12 people in the class. Well, again, that's just 12 factorial, or 12p12. And because we're looking at this as a probability question, we need to take a look at then what are all of the possible ways of arranging people on these 18 bikes. So we have 18 factorial, or 18p18. So our probability of our friends being all together in a row with Allison and Franco on the ends is going to be solved by saying, okay, we have to find out all of the favorable incomes, right? Outcomes, I mean. So favorable, we have 2p2 ways of arranging Allison and Franco, and we have 4p4 ways of arranging their friends, and then we are left with 12p12 ways of arranging the other people to fill the bikes. So this is number of ways to seat the 6 friends in any row. And I write any row, but if I take a look here, I've only done this for one row because it doesn't say they have to be in the front row. They can be the front, middle, or back. So that means we have 3 rows to put these in, so there are times 3 ways of doing that then. On the bottom then is all of our possible outcomes, number of ways to seat all 18. Whoops, that's a bad number. Let me redo that one. Number of ways to seat all 18. So 18 bikes and 18 people would be that 18P18. So this was the same as saying 3 times 2 factorial times 4 factorial times 12 factorial all over 18 factorial. So my 12 factorial will cancel off with part of my 18 factorial and leave me with 3, I guess I can move this down, 3 factorial times 2 factorial times 4 factorial on the bottom. Then I'm left with 18 times 16, times 17 times 16 times 15 times 14 times 13, because I got rid of the 12 factorial and down. So this equals 144 over 13,366,000, and I think that's an 80 that I wrote there. So that works to 1 over 92,820. So the probability of all 4 friends, or all 6 friends being seated on the same, or in the same row is 1 out of 92,820. So again, not very likely. So as I was saying, if you look in the textbook, there are different ways of solving this. I've shown you one of the ways. Some of these questions you can use permutations, some of them can use combinations if arrangement isn't mattering. For this particular question that I just did, I can't remember if it's even in the book or not. Yeah. This one, because it's specifically saying where these people need to be, then you have to use the permutation or just the factorial notation, whichever way you want to look at it. Do your questions.